Hello friends, welcome in the second lecture of colorimetry. So in the first introductory video we have discussed about the introduction of a colorimeter and the principle of the colorimeter, right? Now it is important to understand the instrumentation of the colorimeter. Okay, so let's take a quick recap. So colorimeter, what is colorimeter? If we try to break the word colorimeter, we will end up with here we are measuring the color, right? So it is nothing but our spectroscopy itself, but the addition is here we are only measuring those substances who have color, okay, and those who don't have any color we are coloring them with the help of particular reagent. Okay, so now the question is, what is the need of this coloring agent? Because in UV visible spectroscopy or any other spectroscopy we have not mentioned the need of colorants specifically, right? So why we are using color? So the idea is, whenever we are measuring the OD of bacteria, any kind of bacterial culture, we can do this with the help of turbidity. Okay, but in case of DNA, suppose you are measuring the OD of DNA and protein, there is no such type of difference with the help of which you can distinguish them visibly. Okay, that means suppose I give you DNA in a pen drop tube, and in another pen drop tube I have given you a protein sample. Okay, so by looking them in the naked eyes you cannot distinguish whether what is DNA and what is protein. Okay, now when I will add ninhydrin reagent in the tube where I have I have kept the protein, then you can visualize that yes, it is a protein, right? So that is the idea, why we are using coloration. Okay, and as here we are using coloration and we want to detect the color, so it is obvious that we have to use visible wavelength. Okay, that is another important thing, that for colorimetry we have to use visible wavelength, that is the wavelength from 400 nanometer to 700 nanometer. Okay, and the rest of the thing is exactly same that we have understand in case of our absorption spectroscopy. That means the entire thing is based on the Lambert-Beer law, right? So I have told you the Lambert-Beer law in the first video. So let's talk about the instrumentation, although I will also give a recap of Lambert-Beer law here too. So the first thing is we have to take a light source. Okay, so here the light source will be, remember, most of the cases tungsten filament, and I will also provide notes for the instrumentation of colorimetry too. Okay, so let's keep watching. So first of all we have uses the tungsten filament for the light source. So the light source which are coming from the tungsten filament, remember I have also discussed it in my previous video, that is it is a polychromatic light source, right? And what is polychromatic light? Polychromatic light means light which have various wavelength, right? That means it is a mixture of light where every light have various wavelength. Okay, so now we have used the aperture slit. So what the utility of this aperture slit? Aperture slit will linearize those light together. Okay, because you can see that here the light is quite haphazard, right? From that, when it will pass through the aperture slit, it get linearized. From that, then in the condenser lens we have incorporated, so condenser lens will condense those light source towards a filter. So here the another main instrument is filter. Remember it that in colorimetry you may not use aperture slit condenser lens in some cases, no problem, but there are few things that you have to use. One is light bulb, another one is filter, cuvette photo cell, that is our detector, and the measuring machine galvanometer. Okay, that means this 1 2 3 4 5 instrument is important for colorimetry. Okay, and you are using aperture slit and condenser slit for your accuracy just. Okay, so now the light is passed through the filter. Okay, so now let's concentrate from now. So what is the utility of filter? So I have told you that the tungsten filament provides light of various wavelengths, right? But we need light of a particular wavelength to detect the concentration of the biochemical compound present in the cuvette. Okay, so suppose the concentration is DNA, the biochemical compound is DNA. So we all know that the maximum absorbance of DNA is at 260 nanometer. So we will design our filter in such a way that this filter will only allow the light of 260 nanometer wavelength to pass through. Okay, and the rest of the light will stop here. Okay, because filter will stop them. Okay, so now only the light of 260 nanometer will pass through the cuvette. Okay, and now in the cuvette we have to learn about the Lambert-Beer law. So now when the light will pass through the cuvette, as in the cuvette we have our sample, some of the light will be absorbed by the sample, right? We know sample absorbs any kind of matter in this universe, absorbs light. Okay, and then some of the light will just pass through, right? So now try to understand, if I tell you that the intensity of the light which is entering the cuvette is I0, then can I say that the intensity of the light which is passing from the cuvette will be I? Why? Because it is the light which is coming initially, right? That is why I have used the symbol I0, that is the incident light. Okay, remember it very carefully, because whenever you are going to solve any kind of Lambert-Beer mathematical problems, you have to take care of what is incident light and what is transmitted light. So this one is incident light. Okay, clear? So now after that, the light which is passed through the cuvette will be considered as transmitted light. Obviously it is transmitted through the specimen, right? So I hope you can understand what is the difference between I0 and I. Now you tell me that what will be higher value, I0 or I? So obviously I0 will be a higher value, right? You have to understand this. Okay, so now, so after explaining the instrumentation, I will talk about the Lambert-Beer law. Okay, so now the light is coming to the photoresistor or photocell, that is the detector. When light will fall on the detector, a electrical current will be generated. Okay, remember it, this electrical current is specific for that particular wavelength of light. Okay, now this current will be transferred to the detector, and on the basis of this the detector will give a reading. Okay, and this reading is directly proportional to the intensity of the light. So that is the instrumentation that we have to know to understand the colorimetry. Okay, so now it's time for Lambert-Beer law. So first thing is the Lambert's law. So Lambert-Beer law is exactly a important law for our absorption spectroscopy. Okay, and as here we are using the property of absorption to determine the concentration of the sample, that is why Lambert-Beer law is also applicable here. Okay, so light is passing through the cuvette, no problem. Some of the light is absorbed and some of the light is transmitted through the specimen. Clear? So here scientist Lambert gives a law. Okay, the motive of Lambert's is to is to explain the relation of path length with the absorbance. So now the question is, what is the relation or what is the path length? So path length is nothing but the thickness of the cuvette that you are using. Let's try to think about this. Suppose I have performed a experiment where I want to derive the concentration of the DNA, and you are performing the same experiment, and the sample that you have is exactly the same that I have. Okay, so it is obvious that we should expect that galvanometer reading will be same in both the cases of me and you, right? But the funda is that I have used a cuvette whose path length or thickness is 3 centimeter. Okay, and you have used a cuvette whose path length is 1 centimeter. Okay, so as a result, it was observed the reading in the galvanometer differs in between you and me. So what is the reason why the galvanometer shows various results in case of you and me? So the idea is, let's try to think about this. If the thickness of cuvette is higher, absorption will be higher, because as a result some of the light will be more light will be absorbed by the cuvette and the sample which is present in the cuvette. Okay, that is the reason, and that is the Lambert law. So Lambert law tells us that when the path length of the cuvette increases, the absorption of the light will also increases. That is the generalized form of Lambert's law, that is A varies as L. Okay, and now what is the Beer law? Beer law is similar to the Lambert law. Okay, that means Beer law wants to tell us that if the concentration of the sample that is present in the cuvette increases, the absorption will also increases. Okay, that means absorption is also proportional to the concentration of the sample. Okay, so that is the concept of Lambert-Beer law. When we will join these two formula together, we will get the Lambert-Beer law, that is A varies as LC. Okay, now for removing the proportional sign, we have to use a constant. So here the constant is epsilon. Okay, that is the absorption coefficient. We will going to discuss about absorption coefficient in some another videos. Okay, so here we are getting the result which is directly proportional to the intensity, right? We have get the value. Okay, so I have also discussed it in the previous video that we will get the value in the form of transmittance, right, which is the ratio of transmitted light and also incident light. Why? Because here we have performed the experiment for the sample. Simultaneously we will also run a experiment where in the cuvette there will be only distilled water. Okay, that means there will be a control. Now try to think that in case of control, it will be I0, no doubt about this, but it will be also I0, right, because there is nothing present for the absorbance, right? So that is why when the two value from the sample and from the control goes to the detector, the detector will give you value in the form of transmittance, which is the ratio of transmitted light and the incident light. Okay, so now from this, how can you derive the absorbance? So remember, there is a formula, that is absorption will be log 1 by T. Okay, and here the base will be 10. Okay, from that you can derive the absorbance. But what was our motive? Our motive is to find out the concentration of the biochemical sample, right? So from absorbance we will apply the Lambert-Beard law, which is epsilon LC. Now try to think about this, that L is available and epsilon will be also available and absorbance is available. So this is not a hard task to find out the concentration. Okay, so that is the idea of Lambert-Beard law. Not only that, it is also the idea of our colorimetry and also the absorption spectroscopy. Okay, so I hope you have enjoyed this and you have understood this very well. So thank you for listening to this class.